So example 6. All right, first question is find the temperature at point A. Now, to do this, to do part A of this problem, you have to use the ideal gas law. So PV equals nRT. Look, there's two versions of the gas constant. You know, this is from chemistry. The gas constant, it's 8.31 joules per mole Kelvin. And then the other version of the gas constant is 0.08206. Is that right? Liter atmosphere over mole Kelvin, right? So look, what units do we have here? So pressure, what is Newton per meter squared? A Newton per meter squared is a what? That's a Pascal. And then here we have cubic meter. Both of those are metric. If you multiply Pascal by cubic meter, what do you get? Joule. So which of these gas constants are we using? We're using this one. Okay, so take the ideal gas law, rearrange it for temperature. That's going to be PV over NR. So we're focusing on point A here. So the pressure at point A is 200 pascals. The volume at point A is 20 cubic meters. And then 1 mole, right? We're told right here. 1 mole, N is 1. And then gas constant, 8.31 joule per mole Kelvin. Pascal times cubic meter is joule. So the joules cancel, the moles cancel, and you're left with Kelvin. So this comes out as 481 Kelvin, right? PV equals nRT. Now look, hey, so while we're here, a very common question with these thermo problems, they'll say, what happens to the temperature? So for example, from C down to A, so see how the gas is running this way? What's happening to the temperature from C to A? Well, how do you figure that out? You go PV equals nRT, circle what stays constant. So if we're going from point C down to point A, what stays constant from C to A? What does not change from C down to A? The volume's constant. What else is constant? Moles is constant. And the gas constant is constant. Okay, so what happens to pressure from C to A? Pressure is dropping. So what must be happening to temperature? Dropping. Does that make sense? Okay. Next question. Okay, second question. Calculate the net work done on the gas. So look, there's 3 parts to this cycle. We go A to B, B to C, C to A. There's 3 parts to the cycle. Which part is not doing any work? C to A. C to A does no work because why? The volume doesn't change. The piston doesn't move. Okay? So there's 2 steps that do work. A to B does work and B to C does work, right? Which one's doing more work? So the work from A to B, is it plus or minus? It's minus. I'm going to make that small. And then the work from B to C is bigger. How do I know the work from B to C is bigger? Because the work from B to C, you're taking the area all the way down to the bottom, to the x-axis. What's the work from A to B? The work from A to B is smaller, right? It's just that. So what's the net work going to be? The net work is going to be the difference between those, which is what? The area and the triangle. The area and the triangle is the net work. So to find the work net, you just go 1/2 base times height. So the base of that is 40, right? From here to there, from 20 to 60 is 40 cubic meters. And then the height from here to there is 200. So this comes out as 4,000. And it's plus. Why is it plus? because B to C does more work than A to B, right? Okay, so the work net is 4,000. Okay, part C. Is heat added or removed during one complete cycle? Well, look, what do we know about one complete cycle? So we're on part C here. For a complete cycle, the change of internal energy is what? 0. And why is that? Well, if you start at point A, here, let me revert this, make this clean. So if you start at point A and you go around like this and come back to point A, you're coming back to the same temperature, right? So what's your change in temperature for the whole cycle? 0. What's temperature linked to? Kinetic energy, right? So if the change of temperature is 0 for the complete cycle, that means the change of kinetic is 0 for the complete cycle. Change of internal energy is change of kinetic plus change of potential. What do we never worry about? Potential, that's phase change, right? Potential energy is phase change. We're not going to have phase change. So if the change of kinetic is 0, that means the change of internal energy is 0. Okay, so what's my point here? Hold on. Oh, my point is this. The other equation for change of internal energy is Q plus W. So look, if your change of internal energy is 0, what does that mean about Q and W? They are equal and opposite. Q equals negative W or vice versa, right? So what was our work? The work for this cycle was what? Plus, so what must the heat be? Minus. In fact, this was 4,000, so the Q must be minus 4,000. And I think I just answered part D. Yeah, I just did C and D together right there. So negative 4,000. All right, E. After one complete cycle, oh, they're loving the one complete cycle here. After one complete cycle, is the internal energy of the gas greater, less, or the easy for one complete cycle? Change of internal energy is what? 0 for this reason right here. For a complete cycle, change of temperature is 0, so change of kinetic is 0, which means change of internal energy is 0. And then A, part F here, you guys know what entropy is? Entropy is a measure of disorder, right? Because the gas starts and stops at the same point, it's coming back to the exact same conditions, so the entropy hasn't changed. But what has changed? The entropy of the universe. Do you guys know that the universe is always moving towards disorder? If you clean your room, if you go home and clean up your room, did you lower the entropy in your room? Yeah. But in doing that, what happened to the entropy of the universe? It increased. No matter what you do, the universe gets more disorderly.